then yes, that's d of f is equal to Any questions? Just remember, from the classical calculus term, we're only adding this one term there. Yes?
Why do we have x there? Is it
just to, because the second variable is supposed to be x, and then I don't want to write down partial derivative with respect to a Brownian motion here because it doesn't look good. So it just means take the partial derivative with respect to the second term. So just view this as a function f of t of x, evaluate it, and then plug in x equal bt in the end. Yeah, because I don't want to write down partial bt here. Other questions? Let me close this. Now, suppose this. Consider a stochastic process. X of t such that d of x is equal to mu times d of t plus sigma times d of bt. Okay. So this is almost like a Brownian motion, but you have this additional term. This is called the drift term. And basically this happens if xt is equal to mu t plus sigma of bt, if mu and sigma are constants. From now on, what we're going to study is stochastic processes of this type, whose difference can be written in terms of some time drift term and the Brownian motion term. So we want to do a slightly more general form of Ito's lemma, where we want f of t of xt here. So that will be the main object of study. Now I'll finally state the strongest Ito's lemma that we're going to use. F is some smooth function. And xt is a stochastic process like that. Xt satisfies where bt is a Brownian motion. Then df of t xt can be expressed as it's just getting more and more complicated. But it's based on this one simple principle, really. It all happens because of the quadratic variation. Now I will show you why this form deviates from this form when we replace b to an x. Okay? So remember here, all other terms didn't matter. But the only term that mattered was partial square of f of delta x square dx square. Okay? So to prove this, note that df is partial f over partial t dt plus partial f over partial x d of xt plus half of d of x squared. Just exactly the same, but I placed the dB. Previously, what we had dB, I'm replacing to dx. Okay. Now what changes is dx can be written like that. If you just plug it in, what you get here is, yes, partial f over partial x, mu dt plus sigma of dBt. Then what you get here is 1/2 of partials, and then mu dt plus sigma dBt squared. Out of the three terms here, so we get mu square dt square plus 2 times mu sigma d mu dB plus sigma square dB square. Only this one survives, just as before. These ones disappear. And then you just collect the terms. So dt, there's one dt here. There's mu times that here. And that one will become a dt. So it's half of sigma square partial square of dt. And there's only one dBt term here. Sigma and I made a mistake. Sigma. Yes. Okay. So this will be the form that you'll use it the most, because you want to evaluate some stochastic process, a difference, some function that depends on time and that stochastic process. You want to understand the difference, df. And then the x would have been written in terms of a Brownian motion and a drift term, and then that's the Ito lemma for it. Okay. So, but if you just see this for the first time, it just looks complicated, too complicated. You don't understand where all the terms are coming from. But in reality, what it's really doing is just take this Taylor expansion, remember these two classical terms, and remember that there's one more term here. You can derive it if you want to. So, yeah. But really try to know where it all comes from. It all started from this one fact, quadratic variation. Okay. Because that made some of the second derivatives survive, and because of those, we get these kind of complicated terms. Questions? Okay. Great. Let's see some examples. That's too much of a, there's too much. Sorry, I'm going to use it a lot, so let me record it. Example number 1. Let f of x be equal to x squared. Okay. And then want to compute d of f, fbt. I'll give you like 3 minutes just to try practice. Did you manage to do this? Okay, so it's a very simple example. So assume it's just a function of two variables, but it doesn't depend on t. Well, you don't have to do that, but let me just do that. And partial over partial f over partial t is 0. Partial f over partial x is equal to 2x. And the second derivative equal to 2 at tx. So now you plug in t comma bt. Yeah. And yeah, what you have is mu equals 0, sigma equals 1. If you want to write it in this formula. Okay. So what you're going to have is 2 times bt of dbt plus 1 over 2 times 2 dt. Write it down. So you can either use these parameters and just find that, just plug in each of them to figure it out, or a different way to do it is really write down, remember the proof. This is partial f over partial t dt plus partial f over partial x dx plus 1/2 partial. Remember this one. And x is dbt here. That one is 0. That one was 2x, so 2bt dbt. And you do it one more time, so you get dt. Cool. Does it make sense? Okay, let's do a few more examples. Yeah, just one more. Second one is this. That one. And you want to compute d of f at t comma b of t. So maybe I'll just do it this time. So again, partial f over partial t dt square of dbt squared, which is equal to dt. And let's do it. Partial f over partial t, you get mu times f. This one is just equal to mu times f. Or maybe I'm going too quick. It's mu times e to the mu t plus dx dt. Partial f over partial x is sigma times e to the mu t plus dx, and then dbt, plus, if you take the second derivative, you do that again, what you get is 1/2, and then sigma squared times e to the mu t plus dx dt. Yes?
In the original equation that you just wrote, isn't it 1/2 times sigma squared, and then the second derivative opposite?
Here?
Yes.
1/2.
Times sigma squared.
Oh, sigma. Okay, that's a good question. But that sigma is different. That's if you plug in xt here. If you plug in an xt, where xt is equal to mu prime dt plus sigma prime d of bt, then that sigma prime will become a sigma prime squared here. But here the function is mu and sigma, but so maybe it's not a good notation. Let me use a and b here instead. The sigma here is different from here.
Okay, yeah, that makes a lot more sense.
Yeah. If you replace a and b, then these are yeah. But I already wrote down all mu and sigma. That's a good point, actually. So, but that's when you want to consider a general stochastic process here, other than Brownian motion. But here it's just a Brownian motion, so it's the most simple form. And that's what you get. And this is what you get. It's mu plus 1/2 sigma square And these are just all f itself. That's a good thing about exponential. F times dt plus sigma times d of bt. F. Does that make sense? Okay, and there's a reason I'm covering this example. It's because, let's come back to this question. You want to model stock price using Brownian motion, Brownian process, S of t. But you don't want ST to be a Brownian motion. What you want is a difference, percentile difference, to be a Brownian motion. So you want this percentile difference to behave like a Brownian motion with some variance. Okay, the question was, is ST equal to e to the sigma times b of t? In this case. And I already told you last time that it's not true. And we can now see why it's not true. So take this function, st equals e to the sigma bt. That's exactly when mu is equal to 0 here. What we got here was d of st, in this case, is equal to mu is 0, so we get 1/2 of sigma square times dt plus sigma times d of bt. We originally were targeting at sigma times dbt, but we got this additional term, which we didn't want in the first hand. In other words, we have this drift. Okay. I wasn't really clear in the beginning, but our goal was to model stock price where the expected value is 0 at all times. So our guess was to take e to the sigma bt, but what turns out that in this case we have a drift if you just take naturally e to the sigma bt. So to remove that drift, what you can do is subtract that term somehow, if you can get rid of that term. And you can see if you add this mu to be minus 1 over 2 sigma square, you can remove that term. Okay? And that's why it doesn't work. So instead, use, what is it? S of t equals e to the minus 1 over 2 sigma square t plus sigma of bt. So that's a geometric Brownian motion without drift. And the reason it has no drift is because of that. If you actually do the computation, the dt term disappears. Okay. Question? Okay. So far, we have been discussing differentiation. Now let's talk about integration. Yes?
Could you just, so we do get this solution S of t equals 15.
Mm-hmm.
Could you also describe what it means? So what does it mean, this solution?
This solution?
BT, yes. So does that mean if we have a sample path BT, then we could get a sample path for ST?
Oh, what this means, yes. So whenever you have the BT values, just at each time takes exponential value. Because why we want to express this in terms of Brownian motion is, for Brownian motion we have a very good, pretty good understanding. It's a really good process. You understand fairly well. And you have good control on it. But the problem is you want to have a process whose percentile difference behaves like a Brownian motion. And this gives you a way of describing it in terms of Brownian motion as the exponential function of it. So, Does that answer your question, or?
Right, yes, so distribution means that if we have a sample pad PT, that would give a corresponding sample pad for S of t. Is it like a pointwise evaluation?
Oh, that's a good question, actually. But yeah, think of it as a pointwise evaluation.
Right.
That is not always correct,
Right.
but for most of the things that we will cover, it's safe to think about it that way. Yeah. But if you think about it pathwise all the time, eventually it fails. But that's a very advanced topic. So. So what his question is basically BT is a probability space. It's a probability distribution over passes. So this equation, just look at it, it looks right, but it doesn't really make sense because BT, if it's a probability distribution, what is e to the BT? Okay. Well, basically what it's saying is BT is a probability distribution over passes. So if you take omega according to a pass according to the Brownian motion sample probability distribution, and for this path, it's well defined, this function. Okay. So the probability density function of this path is equal to the probability density function of e to the whatever that is in this distribution. Okay, maybe it confused you more. Just consider this as some path, some well-defined function, and you have a well-defined function. Okay, so what was I trying to do? Oh, integral definition. I will first give you a very, very stupid definition of integration. We say that we define f as the integration if d of f is equal to f dt plus. It's just we define it as an inverse of differentiation. Because differentiation is now all defined, we just define integration as the inverse of it. I mean, given f and g, does it exist? Does the integration always exist? And so on. There's lots of questions to ask, but at least this is some definition. And the natural question is, does there exist a Riemannian sum type description? So that means, if you remember how we defined integral in calculus, I don't know. You have a function f, a very good function f. The integration of f from a to b according to the Riemannian sum description was, you just chop the interval into very fine pieces, a1, a0, a1, a2, a3, dot, 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 and then sum the area of these boxes. And takes a limit. So this was a limit of Riemannian sums. Slightly more, if you want, is it's the limit as n goes to infinity. It's a function 1 over n times sum of I equals 1 to t. I'll just call it 0 to b. F of tb over n minus f of t minus 1. Does this ring a bell? Okay. But question?
You need that subtraction.
No, you're right. Good point. No, we don't. Yeah, thanks. So does integral defined in this way have this Riemannian sum type description? The question. So keep that in mind. I will come back to this point later. And in fact, it's a very deep. It turns out to be a very deep question and very important question. This question, because if you remember, like I hope you remember, in the Riemannian sum, it didn't matter which point you took in this interval. Okay, so that was the whole point. You have the function. In the interval ai to ai plus 1, you take any point in the middle and make a rectangle according to that point. And then no matter which point you take, when you go to the limit, you had exactly the same sum all the time. That's how you define the limit. But really interestingly, like what's really interesting here is that it's no longer true. If you take the left point all the time and you take the right point all the time, the two limits are different. And again, that's due to the quadratic variation, because that much of variance can accumulate over time. Okay, so that's the reason we didn't start with a Riemannian sum type definition of integral, but I'll just make one remark. E2 integral is the limit of Riemannian sums when always take the leftmost point of each interval. Okay. So you chop down this curve at the time interval into pieces, and for each rectangle, pick the leftmost point and use it as a rectangle. Okay. And you take the limit, that will be your E2 integral defined. It will be exactly equal to this thing, the inverse of our E2 differentiation. I won't be able to go into detail. What's more interesting is, instead, what happens if you take the rightmost point all the time? You get an equivalent theory of calculus. So it's just like E2's calculus. It looks really, really similar. And it's coherent in itself, so there's no logical flaw in it. It all makes sense, but the only difference is, instead of a plus in the second order term, you get minuses. Yeah. So let me just make it as a remark, because it's just a theoretical thing, but I think it's really cool. So remark. There exists an equivalent version. Maybe equivalent is not the right word, but a very similar version of E2 calculus, such that basically what it says is dbt squared is equal to minus dt. And then that changed a lot of things. But this far, it's not that important. It's just a fun, like cool stuff. So let's think about this a little bit more, this fact. Taking the leftmost point all the time means, if you want to make a decision for your time interval, so at time t of I and time t of I plus 1, let's say it's the stock price. You want to say that you had like so many stocks in this time interval. Let's say you had so many stocks in times this time interval, according to the values between this and this. In real world, your only choice you have is, you have to make the decision at time t of I. Your choice cannot depend on the future time. You can't suddenly say, okay, in this interval, the stock price increased a lot, so I'll assume I knew it was going to drop, so I'm just going to take the rightmost interval. Like, I'll assume that I only had this many stock. You can't do that. Your decision has to be based on the leftmost point, because the time, you can't see the future. And the reason Ito's calculus works well in our setting is because of this fact. Because it has inside it the fact that you cannot see the future. Every decision is made on the leftmost time. So if you want to make a decision for your time interval, you have to do it in the beginning. So that intuition is like hidden inside of the theory, and that's why it works so well. So let me iterate this part a little bit more. There's the definition of these things, where you're only allowed to, at time t, you're only allowed to use the information up to time t. And there is, I shouldn't have to erase it. So definition. Delta t is an adapted process adapted to another stochastic process xt if for all values of time variables delta t depends only on x0 up to xt. There's a lot of vague statements inside here, but what I'm trying to say is just assume x is a Brownian motion underlying stock price. So your stock is changing. You want to come up with a strategy, and you want to say that mathematically the strategy makes sense. And what it's saying is, if your strategy makes your decision at time t is only based on the past values of your stock price, then that's an adapted process. So this defines the processes that are reasonable, that cannot see future. And these are, in terms of strategy, if delta t is a portfolio strategy, these are the only meaningful strategies that you can use. Okay? And because of what I said before, because we're already taking the leftmost point, this adapted processes just also fit very well with Ito's calculus. It all comes into play altogether. With just a few examples. So first, a very stupid example. xt is adapted to xt. Of course, because at time t, xt really depends only on xt. Nothing else. 2. xt plus 1 is not adapted to xt. Now, this is maybe a little bit vague. So we'll call yt equals x of t plus 1. Yt is the value at t plus 1, and it's not based on the values up to time t. That's a very artificial example. Another example can be delta t equals minimum is adapted. And I'll let you think about it. The fourth is quite interesting. Suppose t is fixed, some large integer, or some large real number. Then you let delta t to be the maximum of x of t delta t, where s of s, where t is from. Okay. It's not adapted. What is this? This means at time t, I'm going to take at it this value, the maximum of all values inside this part, the future. So this refers to the future. It's not an adapted process. Any questions? Okay, so now we're ready to talk about the properties of Ito's integral. Just let's quickly review what we have. First, I defined Ito's lemma. So that means differentiation in Ito calculus. Then I defined integration using differentiation. Integration was an inverse operation of the differentiation. But this integration also had an alternative description in terms of Riemannian sums, where you're taking just the leftmost point as the reference point for each interval. And then, as you see, this naturally has this concept of using the leftmost point. And to abstract that concept, we come up with this adapted process. Very natural process, which is like the real-life procedures, real-life strategies we can think of. Now, let's see what happens when you take the integral of adapted processes. Ito integral has really cool properties. Okay. Okay. So the first thing is about normal distribution. Bt has normal distribution 0 up to t. So your Brownian motion at time t has normal distribution with 0 t. That means if your stochastic process is some constant times v of t, of course, then you have 0 and c square t. It's still normal variable. That means if you integrate, that's the integration of some sigma. Yeah, that's the integration of sigma of dBt. So if sigma is a fixed constant, when you take the Ito integral of dBt, sigma times dBt, this constant, at each time you get a normal distribution. And because integral is like sum in the limit. And this can be generalized. So if delta t is a process depending only on the time variable, so it does not depend on the Brownian motion, then the process x of t equals the integration of delta t dBt has normal distribution. At all time. Just like this. We don't know the exact variance yet. The variance will depend on these sigmas, but still it's like a sum of normal variables, so we'll have normal distribution. That's one fact, and it just gets better and better. The second fact is called isometry. Okay, that was cool. Can we compute the variance? Yes.
Can you put that board up?
Yeah, sure.
Does it go up?
Oh, this one doesn't go up.
Oh.
That's a bad, yeah.
Yeah, so I'll do it later.
I wish it doesn't go up. But okay, so this has a name called Ito isometry. It can be used to compute the variance. So Bt is a Brownian motion, delta t is adapted to a Brownian motion. Bt is a Brownian motion. Then the expectation of your Ito integral. That's the Ito integral of your adaptive process. That's the variance. So you take the square of it. Is equal to something cool. Okay. Your square just comes in. Quite nice, isn't it? Before, I won't prove it, but let me tell you why. We already saw this phenomena before. This is basically quadratic variation. At all time, when you integrate from 0 to t, you get t, and you have t on the right hand side. That's what it's saying. And that was the content of quadratic variation, if you remember. We were summing the squares, maybe not exactly this, but we were summing the squares over small intervals. Okay. Yeah. So that's some really good fact that you can use to compute the variance. Right? You have an Ito integral, you know the square can be computed just in this simple way. That's really cool. Okay, and one more property. This one will be really important. You will see it a lot in future lectures. Is that when is Ito integral a martingale? What was a martingale? Martingale meant if you have a stochastic process at any time t, whatever happens after that, the expected value at time t is equal to 0. Okay? So it doesn't have any natural tendency to go up or go down. No matter which point you stop your process and you see your future, it doesn't have a natural tendency to go up or go down. In formal language, it can be defined as where ft is the events x0 up to xt. So if you take the expected conditional expectation based on whatever happened up to time t, that expectation will just be whatever value you have at that time. Intuitively, that just means you don't have any natural tendency to go up or go down. The question is, when is an Ito integral a martingale? Adapted to v of t, then it's a martingale. As long as g is not some crazy function. As long as g is reasonable. One way you can be reasonable if it's L2 norm is bounded. If you don't know what it means, you can safely ignore it. Yeah. Basically, if g doesn't it's not a crazy function. If it doesn't grow too fast, then in most cases, this integral is always a martingale. Okay? So if you flip it, remember, integral was defined as the inverse of differentiation. So if dxt is equal to some function mu that depends on both t and bt times dt plus sigma of dbt, What this means is xt is a martingale if that is 0 at all time, always. Okay. And if it's not 0, you have a drift, so it's not a martingale. That gives you some classification. Now if you look at a differential equation of this stochastic, this is called a stochastic differential equation. If you have a stochastic process, if you look at a stochastic differential equation, if it doesn't have a drift term, it's a martingale. If it has a drift term, it's not a martingale. That will be really useful later, so try to remember it. The whole point is, when you write down a stochastic process in terms of something times dt, something times dbt, really, this term contributes towards the, tendency, like the slope of whatever is going to happen in the future. And this is like the variance term. It adds some variance to your stochastic process, but still, it doesn't add or subtract value over time. It's really fairly adds variation. So remember that. That's a very important fact. You're going to use it a lot. For example, you're going to use it for pricing theory. In pricing theory, you come up with this stochastic process or some strategy. You look at its value. Like, let's say xt is your value of your portfolio over time. If that portfolio has, then you match it with your financial, let me go over it slowly again. First, you have like a financial derivative. Like option of a stock. And then you have our portfolio strategy. Assume that you have some strategy that at the expiration time gives you the exact value of the option. Now you look at the difference between these two stochastic processes. Basically what it's saying is, when your variance goes to 0, your drift also has to go to 0. So when you look at the difference, if you can somehow get rid of this variance term, that means no matter what you do, that will govern the value of your portfolio. If it's positive, that means you can always make money because there is no variance. Without variance, you make money. That's called arbitrage, and you cannot have that. But I won't go into further detail because Vasily will cover it next time. But just remember that flavor. So when you write something down in a stochastic differential equation form, that term is a drift term, that term is a variance term, and if you don't have drift, it's a martingale. That is very important. Any questions? That's kind of the basics of Ito calculus. I will give you some exercises on it, mostly just basic computation exercises, so that you will get familiar with it. I'll try to practice it. And let me cover one more thing called Gersonov's theorem. It's related, but these are really basics of the Ito calculus. So if you have any questions on this, please ask me right now before I move on to the next topic. Okay. So the last thing I want to talk about today here is an underlying question. Suppose you have two Brownian motions. This is without drift. And you have another B tilde, Brownian motion with drift. So it's just some these are two probability distributions over passes. According to BT, you're more likely to have some Brownian motion that has no drift. Let's say that's a sample pass. According to B tilde, you have some drift. And your Brownian motion move closer to this. Okay. So typical path, it will follow this line and will follow that line. And the question is this. Can we switch from this distribution to this distribution by a change of measure? Can we switch between the two measures? To probability distributions by a change of measure. Let me go a little bit more what it really means. So assume that you're just looking at a Brownian motion from time 0 up to time t, some fixed time interval. Then according to BT, let's say this is pass, a sample pass omega. You have some probability of omega. This is a PDF given by this Brownian motion B. And then you have another PDF, P tilde of omega, where the PDF given by P of t. The question is, does there exist a z depending on omega such that P of omega is equal to z times P tilde? Okay. Do you understand the question? Okay, clearly, if you just look at it, they're quite different. The passes that you get, according to the distribution, they're quite different. So it's not clear why we should expect it at all. And you'll see the answer soon. But let me discuss what all this in the context, different context. Just forget about all the Brownian motion and everything, just for a moment. And this concept, changing from one probability distribution to another distribution, it's a very important concept in analysis and probability just in general, theoretically. And there is a name for this z, for this changing measure. If z exists, it's called the Radon-Nikodym derivative. So before doing that, let me talk a little bit more. Okay, so suppose P is a probability distribution over omega. It's a probability distribution. So this is some set, and P describes the probability that you have each element in the set. And you have another probability distribution, P tilde, another probability distribution. So we define P and P tilde to be equivalent if the probability that A is greater than 0, if and only if, for all. These probability distributions describe the probability of the subsets. So let's just think about a very simple case. Sigma is equal to 1, 2, and 3. P gives 1/3 probability to 1, 1/3 probability to 1/3 probability to 3. P tilde gives 2/3 probability to 3, 1/6 probability to 1/6 probability to 3. So we have two probability distribution over some space. They are equivalent if whenever you take a subset of your ground set, let's say 1, 2. When A is equal to 1, 2, according to probability distribution P, the probability you fall into this set A is equal to 2/3. According to P tilde, you have 5/6. They're not the same. The probability itself is not the same, but this condition is satisfied. When it's zero, when it's not zero, it's not zero. And you can just check that it's always true because they're all positive probabilities. On the other hand, if you take instead, say 1/3 and 0. Now you take your A to be 3. Then you have 1/3 equal to 0. So this means, according to probability distribution P, there is some probability that you'll get 3. But according to probability distribution P tilde, you don't have any probability of getting 3. So they're not equivalent in this case. If you think about it, then it's really clear. So the theorem says, this is a very important theorem in analysis actually. The theorem. There exists a Z such that P of omega is equal to, if and only if P and P tilde are equivalent. You can change from one probability measure to another probability measure just in terms of multiplication, if and only if they're equivalent. And you can see that it's not the case for this. When they're not equivalent, you can't make a 0 probability to a 1/3 probability by multiplication. So in the finite world, this is a very just intuitive theorem. But what this saying is true for all probability spaces. And Z is called the Radon-Nikodym derivative. Our question is, are these two Brownian motions equivalent? The passes that this Brownian motion without drift takes and the Brownian motion with drift takes, are they kind of the same but just skewed in distribution? Or are they really fundamentally different? That's the question. Okay. And what Gersonov's theorem says is that they are equivalent. Also, to me, it came as a little bit not intuitive. I would imagine that it's not equivalent, these two. Just like these passes have a very natural tendency. As you go to infinity, these passes and these passes will really look a lot different. Because when you go really, really far, the passes which have drift will be just really close to your line mu of t, while the passes which don't have drift will be really close to the x-axis. But still, they are equivalent. You can change from one to another. I'll just state that theorem without proof. And this will also be used in pricing theory. And I can't really tell, I'm not an expert enough to tell why. But basically what it's saying is, you switch some stochastic process into a stochastic process without drift. That's making it into a martingale. And martingale has a lot of meaning in pricing theory, as you'll see. So this also has application. That's why I'm trying to cover it. Although it's quite a technical theorem. Try to remember at least its statement and the spirit, what it means. It just means these two are equivalent. You can change from one to another by a multiplicative function. Okay, that's a good place to erase. Let me just state it in the simple form.
Jungle, if I could just interject a comment.
Yeah, sure.
With these sort of changes of measure, it turns out that all of these theories with continuous time processes should have an interpretation if you discretize time and sort of consider sort of a finer and finer discretization of the process. And with this change of measure, if you consider problems in discrete stochastic processes like random walks, basically how, say, if you're gambling against, a casino or against another player, and you look at how your winnings evolve, as a random walk, depending on your odds could be that you will tend to lose. So there's basically a drift in your wealth as this random process evolves. You can transform that process to basically by taking out your expected losses to a process which has sort of zero or change in expectation. And so you can convert sort of these gambling problems where there's drift to a version where there's where the process essentially has no drift, and it's a martingale. And the martingale theory in stochastic process courses is very, very powerful. There's martingale convergence theorems. So you know that sort of the limit of the martingale is basically there's convergence of the process, and that applies here as well. So
You will see some surprising applications.
yeah.
And so try to at least digest the statement. Because when the guest speaker comes and says, by Gersonov's theorem, you actually know what it is in the spirit. Okay, so Gersonov. This is a very simple version. There's a lot complicated versions, but let me just state it. Okay, so P is a probability distribution over passes from 0 t to infinity. What this means is just passes from that stochastic process defined from time 0 up to time t. So these are passes defined by a Brownian motion with drift mu. And then P tilde is a probability distribution defined by Brownian motion without drift. Then P and P tilde are equivalent. Not only are they equivalent, we can actually compute their Radon-Nikodym derivative. So, and the Radon-Nikodym derivative, Z, which is defined as T of P, which we denote like this, has this nice form. It's a nice closed form. Let me just tell you a few implications of this. Okay. So now, assume you have some, let's say, value of your portfolio over time. That's a stochastic process. And you measure it according to this probability distribution. So your underlying, let's say it depends on some stock price, and this stock price is modeled using a Brownian motion with drift. What this is saying is now, instead of computing this expectation in your probability space, so this is defined over the probability space P, or sigma omega P, defined by this probability distribution, You can instead compute it in I missed it. Let's see how it's written. Just you can compute it as expectation in a different probability space. So you transform the problems about Brownian motion with drift into a problem about Brownian motion without a drift. And the reason I have v tilde instead of z here is because I flipped. What you really should have is e tilde here is expectation of z. If you want to use this z. So I don't expect you to really be able to do computations and do that just by looking at the theorem once. So just really try to digest what it means and understand the flavor of it, that you can transform problems in one probability space to another probability space. And you can actually do that when the two distributions are defined by Brownian motions, when one has drift and one doesn't have a drift. How we're going to use it is we're going to use a non-martingale, we're going to transform a non-martingale process into a martingale process. And because it has when you change it into martingale, it has very good physical meanings to it. Okay. So that's it for today. And you only have one more math lecture remaining. And maybe 1 or 2 homeworks. But if you have 2, the second one won't be that long. And you'll have a lot of guest lectures, exciting guest lectures. So try not to miss them.
The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
So let's start with a simple but quite illustrative example. So suppose you're a bookie. And what bookie does? He accepts bets on the horses, sets the odds, and then pays money back. Probably collects a fee somewhere in between. So suppose it is a good bookie and he knows quite well the horses, and there are 2 horses. One horse he knows that for sure one horse has 20% chance of winning and another horse is 80% chance of winning. Obviously, general public doesn't have all this information, so they place a bet slightly differently, and at the end there is 10,000 bet on one horse and 50,000 bet on another horse. Well, bookie is sure that he possesses good information, so suppose he sets the odds according to real life probability. So he sets it 4-1. What would be possible outcomes of the race for him? Monetary. So suppose the first horse wins, then what happens? He has to pay back 10,000 and 4 times more. So he pays out 50,000 and he received 60, right? So he can keep 10,000 out of it. Okay. So what happens is the other more probable horse wins. Well, he'll have to pay back the 50,000 and 1/4 of it, which is 1225. So at the end he'll pay 62,500 while he collected 60,000, right? So in this situation he will lose $2,500. Well, all in all, he expects to make nothing. So he probably could collect enough fees to cover his potential loss. But there is certainly a variability in outcomes. He can win a lot, he can lose some. Now, what if he forgets about his knowledge about the real life probabilities of horses winning or losing, and instead sets the bets according to the amount which were already bet, according to the market, effectively. So what if he sets the odds 5-1? according to the bets placed. Well, in this situation, if the first horse wins, he pays back 10 plus 5 times 10, so 60. He is 0. And if the second horse wins, he pays back 50 plus 1/5 of 50 plus another 10, again 60. So no matter which horse wins, he will get 0, with 100% sure. And if he collects some fee on top of it, he will make a riskless profit. And that's how actually bookies are operating. So it's a simple example, but it gives us a first idea of how risk-neutral framework and risk-neutral pricing works. So we are here not in the business of making bets on horses. We are actually in the business of pricing derivatives. So we'll talk about the simplest possible derivatives, mostly derivatives on stocks, but there are more complicated derivatives which underlying for which could be interest rates, bonds, swaps, commodities, whatever. So a derivative contract is some, in general speaking, a formal payout connected to underlying. Usually the underlying is a liquid instrument which is traded on exchanges, and derivative may be traded on exchanges. Actually, quite a few equity options are traded on exchanges, but in general they're over-the-counter contracts where two counterparties just agree on some kind of payout. One of the simpler derivatives is a forward contract. So what is a forward contract? A forward contract is a contract where one party agrees to buy an asset from another party for a price which is agreed today. Usually, this contract has this forward price is set in such a way that right now no money changes hands, right? So, and here is an example. Well, suppose there is a stock which right now is priced at 80, and this is the forward for 2 years. So somebody agrees to buy this stock in 2 years for this price. And not surprisingly, I somehow set this price such that currently the value of the contract is 0. And we'll see how I'll come up with a price. So this blue line is actually payout, what will happen at the end, right? The payout depending, the graph of F at time t, the termination time or expiry, how it depends on the stock price. Right, so obviously the payout is S minus K, where S is the stock price, so it's a linear function. It turns out that the current price is also a linear function, but slightly shifted, and we'll see how come it's slightly shifted and how much it should be shifted. And K is usually referred as a strike price. Another slightly more complicated contract is called a call option. So if previously the forward is an obligation to buy the asset for an agreed price, call option is actually an option to buy an asset at the agreed price today. You can view it, a call option can be viewed as kind of insurance that against the asset going down. Basically, the payout is always positive. You can never lose money. On the forward, you can lose money. You agree on the price, the asset ends up being lower than this price, but you still have to buy it, right? Here, if the asset ends up at expiry below strike price or out of the money, then the payout will be 0. If, on the other hand, it ends up being above a strike price, or it is called the option is in the money, then the payout will be S minus K as before. So in mathematical terms, the payout is maximum of S minus K and 0, right? And that's what happens at at expiry time, this blue line. So what is the price of this option now? Well, obviously, it should be slightly above, because even if now the asset is slightly out of the money, below strike price, there is some volatility to it, and there is a probability that we will still end up in the money at expiry. So you should be willing to pay something for this. Obviously, if it's way out of the money, it should be zero, right? On the other hand, if it's way in the money, in fact, it should be just as forward. And in fact, it is. We'll see, because if the probability for the asset going back to the strike price and below will be low. And the Black-Scholes equation, the Black-Scholes formula, is exactly the solution for this curved line, which we'll see in a second. Another simple contract, which is kind of dual to call option, is a put option. So put option, on the contrary, is a bet on the asset going down rather than up, right? So the payout is maximum of k minus s and 0. So it's kind of reversed. Also a ramp function at maturity, and here is the current price. Again, even if it's in the money, if it's way in the money, we expect it to be 0. If it's way in the money, we expect it to be slightly below forward, just because of discounting. Okay, so, and here are a few, three main points which we'll try to follow through the class. So first of all, what we'll see that if we have current price of the underlying and some assumptions on how the market or the underlying behaves, there is actually no uncertainty in the price of the option. Obviously, if we fix the payout, right? So somehow there is no uncertainty. It's completely deterministic once we know the price of underlying. The other interesting fact which we'll find out, it's actually risk neutrality, meaning that in fact the price of the option has nothing to do with the risk preferences of market participants or counterparties. It's actually only depends on the dynamics of the stock, only depends on volatility of the stock. And finally, the most important idea of this class, that mathematical apparatus allows you to figure out how much this deterministic option price is now. So let's consider a very simple example, very simple market. 2 periods. So suppose our time is discrete and we are one step before the maturity. So right now our stock has price S0 and there is some derivative F0 with some payout. We'll consider a few of those, right? Also we'll add to the mix a bit of cash, right? Riskless cash, B0, some amount of riskless cash, B0. And riskless meaning that it grows exponentially with some interest rate R. And there is no uncertainty, it's completely, if you have now B0, we know then in time dt, our B0 will grow exponentially. It will become e to the RT. So a bond, basically zero coupon bond. Or money market account, rather. If you go to Cambridge Savings Bank, put $1 in today, then in a year you'll get $1 and basically nothing because the interest rates are 0. So in time dt, we will assume with some probability p, our market can go to the state where stock becomes S1, the price of stock becomes S1, our bond grows exponentially, no uncertainty, and our derivative becomes F1. Or with probability 1 minus p, only 2 states, so our stock becomes S2, bond stays the same, and the derivative is some F2. So let's start with our simple contract, the forward contract. So one can naively approach this problem trying to get the price of the derivative using the real-world probabilities P and minus P, 1 minus P, right? So we know that the payout is S minus K, that's given. So one would say that if we know we are one step before the payout, so let's just compute expected value of the payout using real-world probabilities, get this value. And actually what we are looking here is to set K such that the price now at time t is 0. That's usual convention, so we'll then set K to this probability. To this number, which depends on real-world probability and obviously depends on the stock price at expiry. But obviously we don't know real-world probabilities. We can guess. We can say, oh, the stock is as likely to go up than down. Then it's just an average of and stock prices or something else. But it's all hand-wavy, and actually we never will be right. Instead of doing this, we're kind of following Buki example. Let's try to do something else. Let's think a little bit. So we have a stock which is trading at market now for the price as 0. How about we go to the bank and borrow as $0 right now and immediately go to the market and buy the stock. So right now we are net 0. We borrowed as 0. We paid it immediately to buy the stock. So we have stock at hand. Then we'll wait for one period, and at the same time, sorry, we enter on the short side of the forward contract. So we agree to sell the stock for some price K0. So in DT, in one period of time, the contract expires. We already have stock, so we just go and exchange it for K0 dollars, right? But at the same time, we need to repay our loan, which now had become as 0 times e to the r dt. This is deterministic, right? We borrowed as 0. In time dt, it became s times e to the r dt. So what's our net? The net is K0 minus s times e r dt. So suppose K0 is greater than this value. Then we made riskless profit. There is no risk in the strategy which we proposed. So this is good, but why wouldn't everybody do it all day long? On the other hand, if K0 is less than S0, that's a loss for sure. And if anybody thinks as we did, and we assume that everybody can do it, then nobody would want to enter it. Which means that in order for our forward to be priced 0 now, the strike price has to be equal to this amount, and there is no uncertainty about it. So let's stop and think a little bit. Well, actually, just to see how it works, and that's exactly why I set this K to this number. So, by the way, who can tell me which interest rate does it imply? If our stock price is 80, our strike is 88.41, and the expiry is in 2 years, approximately. 2.5. So in 2 years it will be 5%. So roughly speaking, without compounding, it should be 5% of 80 plus 5%. It would be 84.
Little more than 10%.
So 10% for 2 years. So the interest rate is 5%. Yeah. So yeah, that's actually exactly 5 with but exponentially compounded. Yeah, well, it's a good world probably 5 years ago. That's how it would work. The 2 years interest rates now, the last time I checked was, I think, 30 bips. We can check where the bond is trading now. Okay, give me a sec. Huh? Yep, 32.5 basis points. 1.6 basis points up since the morning. Quite a bit, by the way. So right now interest rates are basically zero. So these two lines would be very close right now for 2 years. In any case, so coming back to our example. So what's important here? How did we arrive to this strike price or to this price of the forward contract? We in fact we took some amount of stock. In this particular case, it was the whole price of stock. We took some amount of cash, and by combining these two pieces, we somehow replicated the final payoff, right? And that's the general idea of risk-neutral pricing and replicating portfolio. What we will try to do in the rest of the class is take a payoff and try to find a replicating portfolio, maybe more complicated, maybe dynamic, such that at the end, this replicating portfolio will be exactly our payoff, right? And what would it mean? Obviously, it would mean that the current price of the derivative should be the price of our replicating portfolio right now, right? And that's how the risk-neutral pricing works. So we are still in this simple situation, but we'll try to price a general payoff F1, a general payoff F, right? And here how it goes. So we still will try to form our replicating portfolio out of the bond, of some amount of bond, and some amount of stock. And we'll say that we will need A, S1, and B of the bond, right? And we'll try to find A and B such that no matter what the real world probability is, we at maturity, at one step maturity, we will replicate our payoff exactly. Unfortunately, in this particular case, it's very doable. It's just two equations with two variables. We should be able to do it. And we can solve it and find this A and B. Then we'll substitute them in this formula, right? Take the current price of the stock, which we know, and some cash, and find the current price of the derivative, right? And this should work for any derivative. It doesn't matter, is it forward, call, put, or some complicated option, as long as it's deterministic at expiry. An interesting way to look at it is to rewrite this formula slightly in such a way, which does remind us taking an expected value, maybe discounting it, because this is expected value sometime in the future. But this probability, and it is a probability because this number Q here is between 0 and 1. But this probability has little to do with the real world, right? In fact, it's something different. But such probability exists. And it's called, the measure where our stock behaves like this is called a risk-neutral measure or martingale measure. And in this measure, as we'll see, the value of the derivative will be just expected value of our payout. And that's what I'm trying to say here. Now let's get into continuous world, right? In continuous world, we will need some assumptions on the dynamics of our stock underlying, and let's make an assumption that it is log normal. What does it mean that it's log normal? It means that the proportional change of the stock over infinitely small amount of time dt has some drift mu and some stochastic component which is just Brownian motion, right? So this dw is distributed normally with mean 0 and standard deviation, which is actually square root of dt. That's how Brownian motion works, and that's extremely important that the standard deviation of Brownian motion is square root of delta t. And that's how it works. So, and again, we will use this idea of replicating portfolio. What would it mean in this case? Well, we would like to find such coefficients a and b on this infinitely small period of time dt, such that by combining small changes in stock with coefficient a and small changes in bond with coefficient b will exactly replicate the change in the derivative, in the payout of derivative. Not payout, in the derivative, in the change of the derivative over this infinitely small time t. Well, to do this, we'll need to use Ito's formula. Did you talk about Ito already? Okay, cool. That's great. So, just to remind you that Ito's formula is nothing more than a Taylor rule, actually, the first approximation up to dt. But because of the standard deviation of the Brownian motion being on the scale of square root of t, we will need one more term there, right? So one term is df dt by dt, another is df by ds by ds, and the square of ds now is actually of order of magnitude of dt. So we'll need a quadratic term there. All right, so this is our df. So what we'll do, we'll differentiate, we'll just substitute it here, right? We'll substitute it here, we'll substitute df, taken from Ito's, our ds, which is like this, and db, and db is, let's not forget that b is deterministic, right? There is nothing uncertain about it, so db is actually rb dt, right? Because our b grows exponentially with interest rate r. So we substitute everything into the formula above. This is just our df with ds expanded and everything, and then we start comparing the terms. One immediate thing to notice that a has to be equal to df over ds for this to hold, right? And if we compare the terms near dt, we'll get this expression here. But that's actually even more the most important part. Then we'll go and use our knowledge that some part of our equation is deterministic, and basically take f and as on one side and leave the deterministic part on the other side, differentiate it once again, and left side will be just rb dt, and if we substitute once again df, and don't forget that what we learned is that a is equal to df by ds, then we collect all the terms and arrive to this partial differential equation, which basically is a partial differential equation for the current price of a derivative, of any derivative, and how it, if we solve it, then we should be able to know the price of the derivative. So now, how do we solve this partial differential equation? Well, yeah. So a few observations about this equation. Well, the first observation is that any tradable derivative, we made no assumptions about the payoff. So any tradable derivative with any payoff should satisfy this equation. The other observation is, as we expected, there is no dependency on real-world drift or any probabilities of going up or down. The only dependence is on the volatility of the stock, right? Not only we found the value of the derivatives, most importantly, we actually were able to come up with a hedging strategy. And what does it mean we came up with a hedging strategy? Well, we found coefficients for any time. We found the coefficients A and B such that we have a replicating portfolio. So what we could do at any point of time, we can hold the derivative, the short derivative, and long the portfolio of stock itself and some cash, and we know how much it should be. Here it's more complicated. We have to dynamically change these numbers as time develops. Every time dt, we will have to rebalance. But both parts will replicate each other perfectly. It's like in a bookies example. We can go to counterparty, agree for some derivative contract, probably with some fee, and then we'll go to exchange and buy the stock, and we will get just cash from the bank, and we'll maintain this at some amount of stock and some amount of cash, and we'll be sure that we are hedged. There is no risk in this combination of the derivative and our hedge. So we will just collect the fee on the transaction. So that's what actually how the business is working. Traders are trading and hedging their positions immediately. I mean, they do take some market risks, but you want to take very, very little and very directional, very specific market risk, and not everything. So our strategy allows us to have a hedging portfolio at the same time, hedging strategy. Another more mathematical but practical consequence is that actually by certain not very easy change of variables, we can take the Black-Scholes equation and put it back to heat equation. Actually, I suggest it as one of the topics for the final paper, for you to do it or check it out in the books and go and understand it. But the good part of it that heat equation is well known and well understood. There are many ways to solve it numerically. For simple payouts for calls and puts, we don't have to do it numerically. But if the payouts are more complicated or the dynamics is different, then numerical methods will be needed for sure. So again, to solve this equation, we'll need, as for any partial differential equation, we'll need some boundary and initial conditions. And these come from our final payout of the option, right, which we know. We know what happens at expiry. And some boundary conditions. For call and put, the final payout is, we know, right? So at time t. And the boundary conditions which we discussed, we can observe them graphically. So basically, for call, as we said, at current time t and boundary 0, it should be 0. The price should be 0, and at infinity, it should be actually the forward price. So it should be just discounted S minus K, discounted payout, right? And similarly for put. So given these conditions, and we can solve the equation. And as I said, for call and put, and for simple dynamics, so Black-Scholes dynamics, log normal dynamics, actually these these equations can be solved exactly meaning up to this term, the normal distribution, which still has to be computed numerically, obviously. But here are the formulas. They do kind of look a little bit, and we'll see about it, that there is some kind of expected value going on, right? One probability times another. But these are the formulas, and that's how I drew the lines on the graphs. And as I said, in fact, the whole world, instead of solving the whole partial differential equation, we can approach it from a risk neutral position and say that in fact the price of our derivative now is just expected value of our payout, discounted probably from the maturity, but not in real time, a real world measure, but in some specific risk neutral measure. And how do we find this risk neutral measure? Well, the risk neutral measure is such that the drift of our stock is actually interest rate. It's riskless. That's exactly how we saw it. We saw it in our binary example, right? So even in our binary example, our expected value of our stock under risk neutral measure, meaning using the risk neutral probability, was drifting with interest rate R. So that the same happens in continuous case. And that's another good exercise, and I would accept it as a final paper, is computing Black-Scholes, deriving the Black-Scholes formula just by taking expected value of the call and put payout with the distribution, log normal distribution, terminal distribution. All right. So for more complicated payoffs, the life becomes more complicated, and some finite differences should be used for more complicated payoffs, or American payoffs, or path-dependent payoffs, tree methods, or Monte Carlo simulations, and that's what's happening in real life. Now, since we have actually plenty of time, I would like to give an example of how replicating idea of replicating portfolio works. I give a couple of more examples. So here is a Bloomberg screen for an call options on IBM stock. It's actually was taken a while ago, a few years ago. So here are different strikes for a call option. The current price of the stock is 81.14, and here are the strikes of the call. So obviously, if the option is way out of the money, meaning the strike is very high compared to the stock price, the value of the option is 0. If it's way in the money, in fact, it is just S minus K. So S meaning being 81, and say the strike being 55, so it's 26, right? So there is some difference, but actually here it's a bit small because the difference should be just discounting, as we know, right? But it's pretty short-dated options. The options they are probably a month long, so there is not much discounting. So it becomes pretty parallel. It's similar here, right? So I mean, this changes by 5, this changes by 5. it's pretty linear, but it becomes nonlinear around the money, around current stock price, right? So we do observe this behavior. But to tell you the truth, if you were to, I didn't put the implied volatilities here, but that's actually you would observe that the world is not black shoals. Meaning that what's the assumption of black shoals? The assumption of black shoals is that every option for any strike on a given stock and a given expiry would have the same volatility, right? So if we went through exercise of implying the volatility according to Black-Scholes formula from the option price which is traded on the market and the current price, we would find out that actually the